welcome back to the lecture series in nanomaterials in agriculture. So, we are into the section of role of nanomaterials in animal production. So, in the last class we started talking about one of the very early work, I should say. It's almost now 18 years back or near about 16 years I would say, of one of the rare earths, what they call as lanthanide series, cerium, Ce. And I introduce you in which part of the periodic table you see this, and I highlighted one of the reactions of nanoceria where we highlighted upon three properties. That ceria is autocatalytic, follows an autocatalytic process, by virtue of which cerium 3 in oxidation state 3 gets oxidized to oxidation state 4, and it again travels back to oxidation state 3 by surface reaction or surface chemical reaction. And this of course needs a little bit of a H plus, or in other words, this needs slightly acidic milieu to make this happen. Now, as I showed you, it is generating free radical generation. It does like this. So, in other words, when we talk about different antioxidant system, natural antioxidant system, so just recollect back when I told you that there are people who started this, and the pioneering people, I would say, if I had to highlight 2 to 3 names, I would highlight Professor Sudip Tusil, Professor James J. Hickman, is the lady Rajlinsky. These are some of the very pioneering people who started this whole area of toying around with cerium oxide nanoparticles. And as I told you in the last class, the autocatalytic mechanism or autocatalysis, this terminology with a pseudo half-life, this whole concept was proposed by Hickman at that time, which is almost 16-17 years back now, around 2000, I would say around 2004, when he proposed this interesting idea. So, what does that mean? What is the biological significance, and where this could be utilized for therapy as well as its animal production application and other biomedical applications? So, in order to understand it, one has to first of all see what all antioxidant enzymes are there in our body. So, let us enumerate the antioxidant enzymes which are present in nature. Okay. So, our body, we are gifted with 3 antioxidant enzyme system. Glutathione peroxidase, superoxide dismutase, which is, in short, they call it SOD. Glutathione peroxidase is GPX in short, and the third one is catalase. These 3 enzyme systems evolve in order to counter the oxidative stress, which is generated in an oxygen biosphere. So, from the time life system has moved from anaerobic to the aerobic world, it started depending on oxygen, and because of the presence of oxygen, it results in lot of oxidative stress, and that is where nature developed a series of antioxidant enzyme, and these three are the key antioxidant enzymes which nature developed over a period of time: glutathione peroxidase, superoxide dismutase, and catalase to counter the oxidative stress. Now, there are several molecules what we used as food additives, as they call it very frequently as antioxidants. Okay. So, there are several you will come across food additives which are antioxidant, and they are added in food, they are added in nutraceuticals, all other things. But the problem with much of these molecules, if you look at these molecules, these will be bulky molecules, like they will be organic molecules with bulky chains and everything. These are fairly bulky molecules which exactly does the same thing what you observe here in this reaction. They takes away the, pulls up or scavenge the free radical by getting oxidized. But now the problem with these kind of molecules are they have a finite half-life, because once much of these molecules, and we are not talking about the enzymes here, okay, we are talking about the naturally occurring antioxidant which are used as food additives. Naturally occurring antioxidant molecules which are used in food industry as food additives. Now, much of these molecules gets broken down over a period of time, and a very short period of time, because they have a finite half-life. They cannot regenerate back, most of them. So, whenever we consume such things, we have to ensure that we are continuously taking them. And of course, you are continuously taking them. What is the quantity, what is the amount? It needs a lot of fine tuning. Now, I propose a situation something like this. Say, for example, we talk about something here, something which has infinite, pseudo-infinite half-life, a molecule like this. So, what is happening? Say, for example, for these kind of naturally occurring molecules, if you are taking in your, as a food additive, say every time you are taking food, you are taking some X amount, okay, and this X amount is like you are continuously doing it in a circular fashion, like you are repeating it, a repetition. Now, I say for example, something has infinite half-life as long as it is in the body, then this molecule which has infinite half-life does not needed to be given repeatedly. So, in other words, if the role of these antioxidant molecules which we are using as nutraceuticals, we are using for healthy development, growth, and so on and so forth, we may not need them to be given so much in amount, and giving a very small amount once or maybe twice over a period of time, those particles will remain there and they will continuously, they will be circulating in your body, or they will sit in different places and they will perform their antioxidative activity over a period of time. Is it possible? That is where the paradigms are slowly calling for a change. Will there be some kind of impact into the system which we haven't thought out? But well, as of now, we haven't seen anything, and we'll unfold the story. So, what we are talking about is, could we use these kind of a small molecule, extremely small, with, if you look at it, this is like, this is out there 5 atoms, 3 oxygen, 2 cerium, or if it is a state 4, then we are talking about 1 cerium and 2 oxygen, like 5 and 3 atoms. We are talking about something way smaller than something which has a lot of these, benzene ring and performing all sorts of antioxidant activity. I mean, even if you look at it, there will be carbon, 6 carbon and another 5 carbon out there. So, I mean, those are huge molecules. Or you can even look for carotene, which has like something like a molecule like something like this, with bunch of single and double bonds stuck together. As compared to that, if you look at CO2, CO2O3, likewise, if you look at it, there is no comparison. These are way too small. Okay. So now that was one of the very early thought which tinkered around that, is it possible to have these kind of molecules. So, having said this, I will add one more thing. When I talked about cerium, I told you this is used as a UV absorbing glass. So, the very first study which called the attention was, it was used. So, all of you are aware of the fact that cerium is being used for, radiation is being used for cancer therapy. Okay. So, say for example, there is a tumor growth here. So, if there is a tumor growth, so this is irradiated with strong radiation in order to destroy this tissue. So, now when you are irradiating that spot, what is happening is that, so you have health. So, this part, if I show the red is the tumor growth, then, and using the green color I am showing the healthy tissue, and I am showing the radiation in say blue. So, what is happening is that how much soever localized you put the beam, there will be beam which will be coming here, and there will be significant damage of healthy tissues all around. Okay. Significant damage of healthy tissue around the tumor or the cancerous growth. Or cancer growth. Okay. So, this is fairly common. So, one of the experiment, very early experiment, there was a wonderful paper, and I will attach that paper for you guys to read, was, if you fortify these with cerium, it was observed that the death of the healthy tissue, that significant damage of healthy tissue is significantly reduced, and you could really get rid of this tumor tissue without causing a lot of harm to the healthy tissue because of its one property, if you remember it, UV absorbing. So, this was one of the paper, came from Tarnuser and Sudhatusil back in say 2005 or 2006, very first paper in the field. As people were tinkering at that time, okay, a very first paper. So, here is one compound which find applications in, of course, which is not mentioned here, something like diagnostic tools and therapy. I am adding one more here, especially in radiotherapy. Okay. And this is a huge problem across the world. Those patients who are suffering from radiation related damage because of removing their cancer, removing their tumor. It's kind of a very tough story out there, the amount of damage it causes. So, that was the very first paper in the field. The next paper which in that aspect came, that came from another gentleman called Papachan Koladakuti in University of Central Florida. Much of this work happened in University of Central Florida. It pretty much, you can say that this molecule took its rebirth in and around the area of Cape Canaveral and all that place, where NASA has its whole launching systems sitting by the Atlantic in Orlando. So, the next came from a gentleman called Papachan Koladakuti, grand old man. What he found out that it has a cardioprotective effect. Okay, the next study in that line, CO2 has a cardioprotective effect. This was another very interesting study which really called up attention. Same time, there were two studies which really put a firm footing about the mechanism of action of cerium. One was on regenerating neurons. Both of them were regeneration or repair of neurons of two places of spinal cord neurons, adult spinal cord neuron, and this other one was for neuronal cell lines of neurons. So, in other words, so the first time it was evolving that it has a cardioprotective, neuroprotective, and this all was except this cell line work which was published in BBRC, and this was published in Biomaterials. So, cardioprotective, it has a role as a radioprotective, and simultaneously it was being highlighted that it has a interesting role in protecting the retinal cells, which goes through a lot of photo damage. Okay, the photoreceptors of the retina, and not only the photoreceptors and retinal neurons where there is tremendous amount of photo damage which is happening every day. Okay. So, some of these studies laid the foundation stone during early, I would say 2004 to 2008, that this molecule could be used for wide array of applications. So, we will continue our story that how these things shaped up some of the very unique applications in animal world. Thank you.